Good afternoon to all. My name is Deepu, and I'm currently a postdoc at TIFR Hyderabad. So this is a work that is part of my PhD thesis I did at Mechanical Engineering, IISc Bangalore. My PhD thesis was on droplet dynamics. We looked at different aspects of droplets, such as vaporization dynamics, its breakup, and so on. For this talk, I'll focus mainly on the oscillation dynamics of droplets. So to begin with, why droplets? So if you look at different applications, wherever you see the sprays in action, sprays are nothing but a cloud of droplets. So, but to understand spray, it's a very complicated picture because we have lots of complex phenomena going on, such as droplet-droplet collision, coalescence, and so on. So as a first step on the way to understanding bigger picture of spray, people actually study isolated droplets. Then, like Daniel was just mentioning previously, we have lab-on-chip applications where here direct applications of droplets and sprays in spray dryers, gas turbine engines, and in nature you have clouds and falling raindrops. So now, why oscillation in particular? So if you look at this example where we have liquid fuel that's being sprayed into a combustor. So there is this liquid fuel that is sprayed using a nozzle, which is called primary. That process is called primary atomization. So the droplets will actually see a very chaotic, hostile environment. So it is subjected to very transient aerodynamic loads. So the droplet will start to exhibit oscillations. And if these oscillations are very unstable, it can grow, its amplitude will grow, and the droplet will further break up. And this is not a secondary atomization, which is very important in determining the fineness of the spray. As you can imagine, if the quality of the if the droplet size distribution of the spray is very fine, then we'll have more surface area to volume ratio, and we can achieve higher combustion efficiency. And there are these applications wherein we have will excite a pendant droplet, and by looking at the frequency of oscillation, we can actually predict its fluid properties such as surface tension, and looking at how fast or slow it decays, we can actually predict its viscosity. Okay, so now coming to my experience, so the question we are trying to address here is, so if you put a droplet in a convective flow field, like in a combustor environment, it will start to exhibit oscillation. But what is exactly causing these oscillations? So if you look at literature, you'll find contradicting theories, such as, for example, some papers will report vortex shedding that's happening in the wake of the droplet, which actually excites the resonant modes of the droplet, whereas some papers will report no association between these two mechanisms. So we were actually trying to investigate what exactly is the mechanism that's causing these oscillations. So here we have a droplet suspended at the center of an air jet, and at some flow rates it will start to exhibit oscillations, and we will record the oscillations using a high-speed camera. And we use different fluids to actually investigate the effect of fluid properties on these oscillations. And for example, we use glycerol in addition to water. Glycerol is like 1,000 times more viscous than water, and there are mixtures which will give you a range of viscosities to play with. And we have ethanol because these glycerol mixtures don't exhibit very high variation with surface tension, whereas ethanol is like has a surface tension that's half that of water. So this is what we see. So if you look at this Reynolds number, so Reynolds number is defined as the mean velocity of air at the droplet location times the droplet diameter divided by the viscosity, kinematic viscosity of air. So for the same Reynolds number, if you compare water and glycerol, you will see that water exhibits very high level of oscillation, whereas glycerol does not. This is expected because glycerol is more viscous, and it will attenuate the energy that's imparted by the air. Whereas if you look at a lower Reynolds number and compare water and ethanol, ethanol on the other hand exhibits very high level of oscillation because ethanol surface tension is very low, so it's very easy to deform and excite the oscillations in ethanol. So this is the same picture, same thing which I said, expressed in a quantitative manner. So this is the aspect ratio of the droplet. As you can see, water exhibits very high level of oscillation compared to that of glycerol. So before moving on to the liquid sphere, let's see what happens if you put a solid sphere in a convective flow field. So if the Reynolds number is less than 300, we'll see the steady separation bubble that's attached in the wake of the sphere. If you increase the Reynolds number slightly higher, we'll start to see slight unsteadiness in the wake of the sphere, and even higher Reynolds number, we'll have the periodic vortex shedding. In this case, it's called hairpin vortices. No, there's a channel actually, and there's a laminar flow, and the flow is from left to right. What do you mean? I think that is a small, this is not our experiment. I took it from the literature, and you can see some sort of attachment here, right? It actually keeps us fixed. So if you look at the vortex shedding frequency, Struhel number is a non-dimensional vortex shedding frequency. And if you plot it against Reynolds number, we are in this regime. You can see as Reynolds number increases, the vortex shedding frequency actually increases. So how do people measure this? They put an anemometer. Anemometer is actually an instrument used to measure the airflow velocity. So if you put an anemometer here, it will actually measure the instantaneous air velocity at that point. And if you take the Fourier spectrum of that, you will see a peak corresponding to the frequency of the vortex shedding. So if you do the same thing with our droplet, what we see is, so this is the FFT of the instantaneous velocity measured in the wake of the droplet. And so this is typical of any turbulent edges. So this is the Kolmogorov minus 5/3 power law that you are hearing from JKB's lectures. So here this is the inertial regime here, where we have the slope k to the minus 5/3, and here is somewhere of the order of integral length scale here. So this is typical of any turbulent air jet, which means that so this shows two things. One is that the air jet is very turbulent in nature, which is expected because it's very susceptible to instability. So it's an open air jet. And then second of all, there is no vortex shedding, periodic vortex shedding happening in the wake of the drop. Because if there were one, we would see a peak corresponding to that particular frequency. So from this, we can actually pull out the theory that vortex shedding is causing the droplet oscillation. So if that is not, then what is causing these oscillations? So to study that, we need to actually look into the droplet shape modes. What we do here is we actually assume axisymmetric oscillations of the droplet, which is actually seen in these images. You can see a left-right symmetry, which means it's axisymmetric. And so we actually decompose the r theta t is the radial location of the droplet air interface as a function of theta and time. So this decomposed into a series of Legendre polynomials. And each of these modes actually represents the standing waves that are fitted on the droplet periphery. So if you look at n equals 2, actually there is a black curve here which actually shows the undisturbed droplet shape, which corresponds to the spherical shape of the droplet. So n equals 2, as you can imagine, is a standing wave. So this actually represents the Prolate-Oblet oscillation of the droplet. And this is a result from Rayleigh, who actually predicted the natural frequency of each of these modes. So if you look at this, gamma is a surface tension, which is like a restoring force, like a spring constant. And here we have the mass of the droplet. So this is something like root of k over m sort of resonant frequency. And this is the resonant frequencies for the different fluids that we have used. So this is all of 100 hertz. I'll skip all this. So to cut a long story short, so what we have seeing here is that, so if you look at the spectrum of the air jet, you can see it contains very high energy up to the order of around 200 hertz, and which covers the resonant frequency of the fundamental mode of the droplet, which is 100 hertz. So this air jet is actually exposing the droplet to a wide range of frequencies, which includes the resonant frequency of the droplet, and the droplet starts to get oscillated at the resonant frequency, because it's very easy to excite something at its resonant frequency. So this is the principle of any natural system. If you pluck a guitar string, for example, you're not exactly exciting it at its natural frequency. You're dumping a cocktail of frequencies from which it will start to get oscillated at its resonant frequency. I think I'll skip all this. I'll just quickly move on to an analytical model, which we use to actually corroborate our hypothesis. So basically, we start with the Navier-Stokes equation, which is the momentum equation for a fluid, and all the boundary conditions. And we do the same decomposition here of the shape of the droplet. And here, epsilon actually shows the smallness of the amplitude of oscillation, which means we are assuming a linear oscillation of the droplet. So basically what you'll end up with is a dynamic equation telling you how each temporal coefficient of the mode will vary with time. So you have an inertia term here, then dissipated term which is proportional to fluid viscosity, then you have a restoring term proportional to surface tension. And not surprisingly, we have the dynamic pressure of the external air jet or aerodynamic loading coming as a forcing in the equation. And if you solve this, and if I compare it with the, so this is again the PSD, or power spectral density, or the frequencies FFT of the second A2 mode, which we are considering only the second mode because that's a fundamental mode of droplet oscillation. And but whatever I'm saying is true for all higher modes of oscillations. So here, if you compare so the black curve corresponds is the PST we got from the AT from the model, and here we have experimental PST as well. And as you can see, the model is capturing the resonant frequency very accurately. But the second peak here, which I didn't get time to talk about, is actually the subharmonic response of the oscillation. Because if you look at the oscillations of the droplet, for example, it exhibits very large level of oscillations. So if you look here, you have very, the fluctuations of oscillation itself is comparable to the mean, which means it's highly nonlinear in nature. And so as a result of that, we are seeing a subharmonic response. So if it were a linear, spring mass damper system, we won't be able to see this subharmonic response. So the model is a linear model, so it's able to actually capture the linear characteristics of the oscillations, where the nonlinear subharmonic response is not able to capture. I think I'll stop at this point. Right. Yeah, that's the whole point. So this jet, so we are keeping the droplet at the center of an air jet. And this air jet is turbulent, which has energy spread out across all scales, all frequencies. Yeah, that's acting as a force. So the pressure fluctuations, or the turbulent fluctuations in pressure and velocity. So that's how I do the modeling also. So the external pressure I model as a fluctuating parameter. Right. 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 Yeah, it should be Reynolds number, but here Reynolds number I've used that of air. So if I use the Reynolds number of the fluid itself, I think that's the right parameter to compare. So here I use Reynolds number as a characteristic of the aerodynamic loading. You understood? So if here nu is the kinematic viscosity of air. So if I use nu as of the fluid, so that is so basically it's the aerodynamic loading force, aerodynamic force divided by the viscous force that's set up in the fluid. Right, right. Yeah, so there we had used Weber number, something like Weber number to actually characterize the effect of surface tension, yeah. This is exactly viscosity, oops. So this, yeah, because U infinity D, this is common, same for all the fluids. D is the diameter of the droplet, U infinity is the mean flow rate. So that is same across all the fluids, only viscosity, okay, viscosity is also same. Okay, so yeah, in that case, yeah, so viscosity ratio I have not plotted here. So basically, you can see glycerol has a viscosity of 1000 compared to water. So that's effect is what's shown here. Yeah, it matters. So that's what we are seeing here, right? So if you take viscosity with respect to water, so glycerol has a viscosity of 1000, and that leads to this much of change in oscillation levels.